Good.
Question 9b. A rectangular conducting slab is infinite in x and z directions and extends between negative y0 to positive y0 along the y-axis. Piece of y is equal to p0 y squared. B. Find the distance y from the center of the slab and solve for E when y is greater than y0. Okay, so we know that Gauss's law is the charge density times the area is equal to Q sub E over epsilon naught. So here I drew my picture of this slab and the cube from question 8. So you can see the limits negative infinity to infinity, negative y0 to y0. We have our width W, and D is going to be used as the length. So first we're going to tackle the right hand side, and we know that the right hand side is going to be the same as number 8. It's going to be charge times the area, but the area can only be the tops and the bottom squares because these are infinity. Those are going on forever, so we have to take the areas of the top and the bottom and add them together. So that takes care of the left side here. Then we're going to go to the right side, and it wants to know the distance from the y, but the problem simply states that a piece of y is no longer constant. It's going to be changing, so we're going to have to take the triple integral like we learned in class on Thursday. So it's going to be 1 over epsilon naught because of the QE over epsilon naught, and QE simply becomes the triple integral of the integral from negative a to a, integral of negative b to b, negative y naught to y. P naught y squared is the equation here, times dy, dx, dz, each respectively to these limits. Now that leads us to this. So we're going to set the equation up just like we did up here, only adding in the areas of the top squares, d times w, which is d times w, the length times the width of each square, to find the areas, is equal to 1 over epsilon naught times the integral from negative z to z, negative y to y, and negative x to x. Each respectively, as you can see, because we go z, dz, y, dy, x, dx, and then our equation here, p naught y squared. That's the main equation here. Basically, we just have to find our limits, and then we can solve if we were to have variables. So I redrew a picture here, so we have y coming this way, d going this way, and our y naught going up and down with respect to the axes, as you can see in the red lines. And we're going to use negative d over 2. We're going to use d over 2 and w over 2 because if we use the full values, it'll just cancel out and will give us an answer. So I'm going to go back up here and I'm going to say, hey, this is dx. Those are my x values. So my x values here are my w's. So I'm going to replace the x with negative w over 2 to w over 2. And I'm going to do the same thing with y. So when I look at my y values here, I'm going to look at my y values, and that's going to be, hey, that's negative y naught to y naught. When I go to my z values, I'm going to look at those, and I'm going to say, oh, that's my negative d over 2 to d over 2. So here we have our limits simply right there. Which brings us to the next part. We have our equation, E times the area of the top and the bottom of the square, the sides are infinite, we can't take those into account, times equals 1 over epsilon times the triple integral from negative d over 2 to d over 2, negative y naught to y naught, negative w over 2 to w over 2, times p sub naught times y squared, which was the original equation, times dx, dy, dz, each respective to these corresponding limits. So basically, we just solve for E by dividing this area up here. We weren't given specific numbers in the problem, so we're solving for E generically, which is going to be E is equal to this whole integral right here, divided by this dw plus dw, which is the area of the top and the bottom squares, all on the bottom. And if we were to have our values in the original problem, like values for length and width, then this would be a very easy problem to solve because we would just take the integrals of the x and y and z respectively, which would give us, you know, x, y would turn into y cubed over 3, and z would be z. And you'd plug in your respective variables for these, because these would be actual numerical values. That's the problem. Thank you.
Damn, dude.